for this problem, we'll be going over pressure and temperature in relationship to a different altitude. So we start at a pressure and temperature, say the pressure at sea level, whatever temperature it is, and we change our altitude to go, say, to the top of Mount Everest or something like that. That pressure and temperature will change. The question is, can we make an equation that can relate it like that? First thing to go over, first thing that pops into my mind is the basic equation of statics, and that looks like this. So first things first, gravity, constant, pretty straightforward. We have the difference in pressure over the difference in altitude, z, height, position, whatever you want to call it. Then we also have this density. We can rewrite this density using ideal gas laws. Because density is just mass over volume, we can substitute the volume in. And then on top of that, to get rid of the number of moles and account for mass, we can multiply by the molar mass in kilograms per mole. So let me write that out. And we're also going to simplify the sides of this real quick. So that gives us this equation. So first things first, we want that pressure-temperature relationship. So we're going to move the P over T, which will turn into T over P, to this side, and we want to move this dz out of there so that we can integrate. So let me write that out. Awesome. So the only problem we have here is that we are differentiating P with relation to a T, but if we take that integral right now, we would still have this relationship of a final temperature and a final pressure with an initial pressure and an initial temperature, which isn't really helping us. And the reason we have a problem with that is because we know our initials, which is fine, but then we have a final temperature and pressure, so we need to know what one or the other is. So how are we going to move this? Well, we'll start here. We know that at a very high level, that thermodynamics, the internal temperature between gas particles isn't exchanging, so the heat isn't exchanging. So we can use the first law of thermodynamics for internal energy. So as I mentioned earlier, delta Q, transfer of heat, is equal to 0. There's no transfer, so we can disregard that part. Again, we know that this P can be fixed up using the ideal gas law, and that N doesn't matter because this equation is on a per mole basis, because we don't want to deal with imbalanced moles. We want that nice ratio. Next, we know that from mass and energy balance that this du, the differentiation in internal energy, is basically just CV dt. So we're going to write that in. I'm also going to take t to the other side so we can integrate. So as we mentioned, this is a change in temperature to a change in volume relationship. Over here we have a change in temperature and a change in pressure relationship with altitude, which this is what we want, but we need that T. But the problem is here we have volume. So you'll see eventually we're going to change that out. So let's do the integration and we'll get to that step. So here, a couple things. We can do basic division and get this into an exponent above the natural log before we raise everything to the power of e and get rid of the natural logs. And on top of that, we can change around these volumes of V2 and V1 to give us essentially a R of T2 over P2, etc. for 1 as well. So now we just need to move over this T value to get T's relationship to P real quick, and also to sort out this exponent. So give me a second to do that. Okay, two things. Did the reciprocal to set this exponent up, and we're also going to evaluate both of those exponents because we need the specific heat ratio, because eventually we want to set these up because we need something to solve for T. So these T2s are our final, so we're actually just going to get rid of that, and these T1 and P1 are our initials, which is all good. So what we want to do is we want to know what this relationship is. This relationship right here, 1 plus RCV, this is actually K, which is basically just CP over CV. So if this is K, this is basically just this minus 1. So this becomes K minus 1. So let's write that in real quick. So that setup, we can solve for T really easily. Boom. We have a relationship of our final temperature with pressure, and we can move that over here to then get their relationship with a change in altitude. So let's write that in real quick, and we can set up this integral and make it look a little nicer. Go ahead and do the integral on this side. Now this part can be pulled out pretty easily, and then we can set up the integral for the next step. Before I do that, the whole thing here is that this, we now have the change in pressure, we now have a controlled T. So this is now a relationship. So we built that relationship so we don't have to worry about finding that second input, and we'll only spit out a different pressure output, which we can get that pressure to then solve for temperature using basic ideal gas. So let's write this one out real quick. So I'm gonna skip a step real quick, and I'm just gonna move this over to the other side to clean it up a little. Awesome. So we can get rid of it on this side. So now we have to deal with this integral. So now one thing to notice here, those two are not exactly going to cancel out, but the exponents are going to work their way out. So once we do that math and we move this over to the other side, we'll get our final answer. So now we have our starting pressure with the ratio between the specific heats, with our starting temperature with its relationship to a change in altitude, which will give us our final pressure or our changed pressure, which then we can use in a basic ideal gas equation to figure out our final temperature as well. So that successfully relates the pressure and temperature with the change in altitude.